Year 13, Further Algebra, Lesson 1, Revisiting Binomial Expansions and Pascal's Triangle. So we're going to start off by revisiting the concept of Pascal's Triangle. Let's start by layering up and building the triangle. So, as you hopefully remember, the first number in Pascal's triangle is a 1. Now, underneath that, we then have a 1 and a 1, and we can then start generating the pattern. We have 1, 2, 1. So every number in Pascal's triangle is created by adding together two preceding numbers diagonally up above it. So the next row of Pascal's triangle, 1, 3, 3 and 1, and hopefully you can see that the 1 and the 2 here add together, contributing to create that 3. Let's add in a few further rows of Pascal's triangle. So we then have 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6 and 1. And it's very quick and very easy to build up the first few rows of Pascal's triangle. So in the past, you've used Pascal's triangle to carry out binomial expansions. And what we're going to do is revisit some of the work that you have covered in year 1 of the A-level course. So the first example that we're going to look at involves us expanding 1 plus 2x to the power of 5, and we're going to do the expansion using Pascal's triangle rather than using the binomial coefficients calculated on the calculator just yet. Now, what do we need to observe? Well, first of all, we need to check the power involved. It's 5, so we want this row of Pascal's triangle, the 1, 5, 10, 10, 5, 1 row, and we're going to start writing out the terms of the expansion. Now, I am going to split up the parts of the binomial, so I've got 1 here, and then of course, signs are important. Here I have a positive 2x, and I'm going to list the terms vertically one by one rather than in a horizontal row, because it's a lot easier to keep track of the different terms when they're listed in this way. So let's do this. I might be putting in more working than you would usually do here, but that's okay because I'm just really trying to make it obvious as to how we do this expansion. So we take the coefficients from Pascal's triangle, which means we start with a 1. We then take the first part of the binomial in the expansion, which is 1, and I'm going to raise this to the power of 5. I then take the next part of the binomial, which is 2x, and this will be raised to the power of 0. And this will give me my first term. I'll then add to that the next term. Now, how do I start generating the next term? Well, I take the next coefficient from Pascal's triangle, which is a 5. I then take 1, raise it to the power of 4. So the powers of 1 descend. The powers of 2x ascend. So look at the pattern. Next term, I want the next coefficient from Pascal's triangle, which is 10. 1 would be raised to the power of 3. 2x would be raised to the power of 2. So look at the red terms. You can see the powers of 1 are descending 5, 4, 3, 2, 1, 0 in a minute, and the powers of 2x are ascending or increasing 0, 1, 2, 3, 4, 5 in a minute. The blue numbers represent the coefficients taken from Pascal's triangle. So what's next? It's another 10 multiplied by 1 to the power of 2 multiplied by 2x to the power of 3. And I will fill in the next two terms as well. So I've completed the rest of the expansion here. Now, some of you may be wondering why I've bothered to write in terms like 1 to the power of 5 and 2x to the power of 0. I've just done that so that you could see the pattern. If I were perhaps answering an exam question on this later on, I probably wouldn't necessarily include that because it's very clear that you've done the expansion. I just wanted you to see the terms clearly. So we're now going to write out the expansion in full, and it is 1 plus 10x plus 40x squared plus 80x cubed plus 80x to the power 4 plus 32x to the power of 5. Now, be very careful when you are simplifying. Of course, there are certain things that you can do to make life a lot easier for yourself. Anything raised to the power of 0 is equal to 1. And of course, as we've said, all of these red terms here, they all equal 1, so that's not necessarily something you have to worry about particularly. Where I think people need to be more careful is, for instance, when evaluating 2x to the power of 2, remember it's 4x squared, not 2x squared. Same here, 2x to the power of 3 is 8x cubed, so be very careful as you expand these terms and make sure that you do not write in any errors. Now, let's just quickly revisit the blue values, which were the coefficients of Pascal's triangle. Now, hopefully you will remember that these are also called the binomial coefficients, and you can generate them using your calculator. For instance, 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. So using the appropriate buttons on your calculator, you can generate the binomial coefficients. Now, in case anyone has forgotten how to do this on their graphical calculator, remember the buttons that you need to press to access the binomial coefficients. You need the option or OPTN button first of all, and you then need to press F6, which is the forward arrow that takes you onto the next menu. You then want prob, which is accessed via the F3 button, and then you can see the NCR or nChooseR button, which is also F3, which you can use to generate any binomial coefficient. Now, people often ask, when should you use Pascal's triangle and when should you use the binomial coefficient option? Well, if you're doing an expansion and the power is around 5 or fewer, Pascal's triangle will still be a very efficient way of doing this. If you're looking at much larger powers of the expansion, you may well choose to use the binomial expansion as it's a more efficient way of performing the expansion. So let's look at another example. We are going to expand 2 minus 3x squared all cubed. So instantly a trickier example than the previous one. There's a negative sign involved. Part of the expansion is also 3x squared. Now, because the overall index is low, it's 3, we're going to make use of Pascal's triangle to do this. So we need this row here, 1, 3, 3, 1, to do our expansion. So again, I'm going to list the terms vertically, and we'll then collect them together and simplify at the end. So let's have a look at how we're going to do this. So the first coefficient of Pascal's triangle, here the first binomial coefficient is 1. Now in my expansion, I have here a 2, and then I must remember that this is not just 3x squared, it's minus 3x squared, and I've got to make sure I keep that negative sign involved as I take each of the powers. So I've got 1 to begin with, and then I'm going to have 2 raised to the power of 3, and then I'm going to have negative 3x squared all to the power of 0, which of course is just going to be 1. Now I could have started with the indices the other way around. I could have started with 2 to the power of 0 and negative 3x squared to the power of 3 and swapped the increase or decrease, but I've just chosen to start it this way. It doesn't matter as long as you're consistent. So the next term is going to have a binomial coefficient of 3 from Pascal's triangle there. We're reducing or decreasing the powers of 2, so this becomes 2 squared. And we then want to multiply by negative 3x squared to the power of 1. So the powers of 2 are descending, the powers of negative 3x squared are ascending. Let's keep going. Next coefficient, 3. Then we want to have 2 to the power of 1 and negative 3x squared all squared. And then one final term, 1 multiplied by 2 to the power of 0 multiplied by negative 3x squared all cubed. So again, make life easier for yourself when you do the simplification. Anything to the power of 0 is just a 1. So we can exclude these from our simplification, and we're then just going to simplify the rest of the terms really carefully. So as you do this, please be very careful with your simplification. So for instance, if you're working out negative 3x squared all squared, remember that that is negative 3x squared multiplied by negative 3x squared, so that will give you 9x to the power of 4 as part of your expansion. Similarly, negative 3x squared all cubed, well, we have to cube each part of that, so cubing the negative 3 will give us negative 27, and then cubing x squared will give us x to the power of 6. So you may wish to have a go at simplifying the expansion and then checking your answer at the very end. So let's have a look. We've got 8 for the first term. For the second term, we have negative 36 x squared. For the next term, we have plus 54x to the power of 4. And for the last term, we have minus 27x to the power of 6. So let's have a look at another example that you might have come across in your work last year. Read the question carefully. We are going to find the coefficient of x to the power 4 in this expansion, 5 minus 2x all to the power of 6. Now, my first word of warning here, do not expand the whole expansion. It is completely unnecessary and a waste of time. You do not have the time to do this in an exam, and if you do that, you will find that you have wasted too much time on something you don't need to do, and you will not have enough time to address the rest of the question. So take that warning as a serious one. If you're just trying to find one term or one coefficient of a term in an expansion, don't do the whole expansion. Be smarter than that and think more carefully and logically. Now, let's take a look at the expansion that we are doing. So it's to the power of 6, which means we would be looking at this row of Pascal's triangle. Now, the term that we're interested in is x to the power of 4. Now, the x part of the expansion is going to come from here, this negative 2x. Of course, there's also a 5 involved in the expansion as well. So let's start to write out what it might look like. Well, to get a power of x to the 4, we would have to have negative 2x, and it would have to be raised to the power of 4. Now, think about the rules. When you're doing your expansion, the other part of the expansion has got to have an index which adds up to give you the overall index, which is 6. So if negative 2x is being raised to the power of 4, that means that 5, which is the other part of the expansion, has got to be raised to the power of 2, so that the 2 and 4 add up to the overall power of the binomial expansion, which is 6. Now, what is the binomial coefficient then going to equal? Well, let's look at the coefficients in a bit more detail. We've got 1, 6, 15, 20, 15, 6 and 1. Now imagine we were looking at the powers of x and we were starting with the lowest power of x. So x to the 0, x1, x squared, x cubed, x to the power of 4, x to the power of 6. And you can see straight away that the coefficient that we want, if the term is x to the power of 4, is going to be 15. So we can just easily fill in a 15 using that method there. Now, what would have happened if you'd started the expansion with x at its maximum power and then reduced it? Well, if you'd done that, let's see what would have happened. X to the power of 6, x to the power of 5, x to the power of 4. So again, that would lead you to a binomial coefficient of 15. Well, let's think about those binomial coefficients and what they mean in a bit more detail. So the first one is, of course, 6 choose 0. 6 choose 1, 6 choose 2, 20 is 6 choose 3, 15 is 6 choose 4, 6 is 6 choose 5, and 1 is 6 choose 6 squeezed in on the end. Now remember the ones that we have been interested in. It's this, 15 here and 15 there. Now that's 6 choose 2 and that's 6 choose 4. So because of the symmetricality of Pascal's triangle, it doesn't really matter which one we choose, but what we can do is ensure that we're choosing 6 choose 4, which of course has a 4 that matches the power of x that we are looking for. So that 15 can come from Pascal's triangle, or it can come from our binomial coefficients and from us choosing 6 choose 4. Or alternatively, 6 choose 2 would also have given us exactly the same answer if we'd been working in the other direction. Now, let's work this out. So we've got 15 multiplied by 5 squared, which is 25, multiplied by negative 2x all to the power of 4, which is of course 16x to the power of 4. But remember, the original question asked for the coefficient, not for the term. So at the moment, this is the term in x to the 4. What we want is the coefficient, so we want the product of those three values here. It's an easy way to lose a mark in an exam if you're not careful or if you're not thinking and if you don't understand the difference between the two pieces of vocabulary. So the coefficient is 15 multiplied by 25 multiplied by 16, which is equal to 6,000. So let's have a look at another interesting question. We're going to find the term that is independent of x in this expansion. So let's take a look at the question. The power involved is 4, which means we need to make sure we're looking at this row of Pascal's triangle. Now, when we carry out this particular expansion, because one of the terms is x and the other term is a 1 over x term, there will be a point at which a cancellation of the variable occurs and we end up with a term that does not contain x. So if you think about the structure of the terms, we'll start off with x being raised to the power 4 and minus 2 over x being raised to the power 0. We then have x cubed and minus 2 over x to the power 1. X squared and minus 2 over x to the power 2. Now here is the point at which you should stop and think, because when you square negative 2 over x, what will you get? Well, you'll get 4 over x squared. And if you're multiplying that by x squared, that is where the cancellation occurs. Now it's important that we include the correct coefficient from Pascal's triangle, so 1, 4, 6. So this is the overall term that we are looking at. Let's simplify it a little bit further. Let's take that over here. So we have 6 from Pascal's triangle. We have an x squared, which is part of the expansion. And as we know, we have 4 over x squared for the other part of the expansion. So the x squared will cancel here and here, and this leaves us with a term of 24 in our expansion. The other terms will all be different powers of x, and they will all contain an x. So this is the only term in which the cancellation will occur. So we're now going to spend a little bit of time thinking about binomial coefficients and what they actually mean. So we've all come across the concept of n choose r, which sometimes you see written a little bit like a vector, meaning the same thing. Now, how is a binomial coefficient calculated? Well, when you learnt about this topic in year 12, you derived a formula for calculating a binomial coefficient, which is n factorial over r factorial n minus r factorial, and that's how each binomial coefficient is calculated. Now, you might need to remind yourself about the concept of a factorial. So, for instance, if I want to work out 4 factorial, that would be 4 multiplied by 3 multiplied by 2 multiplied by 1. So 4 and all integers below 4 multiplied together to create a product. So 4 factorial is equal to 24. Now, we're going to work out some general binomial coefficients. So n is going to be n, and I'm going to choose specific values of r. So let's think about n choose 0, first of all. Simplest possible example. Now I'm going to input the r values into this formula here. So n choose 0 would be n factorial over 0 factorial. Now, n take away 0, all factorial. How does that simplify? Now, you may have covered last year, hopefully you covered last year, the fact that 0 factorial is defined to be equal to 1. And we'll need that fact as we work this out. So, this is now equal to n factorial over 1 multiplied by, now n take away 0 is n, so this simplifies to n factorial as well in the bracket. Now what happens here? Well, n factorial would cancel with n factorial, and the whole thing would simplify down to 1. Now, why does this make sense? Think about what n choose r actually means. It's asking you to calculate the number of ways in which you could create combinations of r objects from a choice of n. How many different ways are there of making a combination if you have r items within your combination and you are choosing more broadly from n in total? Well, here we're being asked how many ways can we choose 0 objects from a total of n objects? Well, there's one way in which you can do that, and that's to choose nothing at all. So it makes sense that n choose 0 is equal to 1. Also, think about Pascal's triangle, and in Pascal's triangle, the first number in each row is always 1. So for instance, this is 3 choose 0. So anything choose 0 will always be equal to 1. Let's work out another one. N choose 1 this time. So applying our formula again, remember generalised n, that's n factorial over 1 factorial, and this time n minus 1 in brackets all factorial. Now 1 factorial is simply equal to 1, so that's not very interesting, but n factorial over n minus 1 factorial is interesting. Because what does n factorial actually mean? It means 1 multiplied by 2 multiplied by 3 multiplied by all of the numbers up to and including n. Now the number before n is n minus 1, so I'm going to write it in like that. So that's what n factorial is equal to. And we're dividing this by n minus 1 factorial, which is 1 multiplied by 2 multiplied by 3 multiplied by all of the numbers up to and including n minus 1. So what's going to happen? Well, a very interesting cancellation. All of these numbers will cancel with all of these numbers, and you're left with an answer of n. Now again, that should make sense when you think about Pascal's triangle. So if I take this value here in Pascal's triangle, well, this is equal to 3 choose 1. And that's equal to the n value. Let's think about it logically again. What does n choose 1 actually mean? It means the number of ways I can choose one item when I have a total of n items to choose from. Well, there are n ways I could choose one item because I could choose each of the n items. So that's why n choose 1 is always equal to n, and it doesn't matter what your value of n is. And again, think about Pascal's triangle. The second item in each row of Pascal's triangle is always the value of n. So, what about n choose 2? A little bit more complex here. So this will be equal to n factorial over 2 factorial n minus 2 factorial. Now, what I'm going to do is I'm going to rewrite n factorial in the numerator as 1 times 2 times 3 times all of the numbers up to and including the numbers that come before n. So that's n minus 2, n minus 1 and n being the last number in that list. Now this is all over a denominator. I'm going to leave 2 factorial as it is, but I'm going to rewrite n minus 2 factorial as all of the numbers up to and including, all of the integers I should say, up to and including n minus 2 multiplied together. Let's look at the pattern of cancellation here. All of these numbers will cancel in the division, and you're left, very interestingly, with an n and n minus 1 in the numerator and a 2 factorial in the denominator. So, can you do something similar for n choose 3? Can you write it out in terms of the factorials and then cancel down and see what it simplifies to and then identify if there is a pattern? Have a go yourself, the answer will come up in a minute. Let's see if you got this right. So n choose 3 is equal to n factorial over 3 factorial n minus 3 factorial. Let's write out what the numerator is. It's 1 multiplied by 2 multiplied by 3 multiplied by etc. All of the numbers up to and including n. So I'll go back to n minus 3, n minus 2, n minus 1 and then n. That gives us a little bit of clarity when we're trying to cancel. And this is all over, and I'll leave 3 factorial alone. But I will write out n minus 3 factorial, so you can see the products of all the numbers up to and including n minus 3. Look at the cancellation here and here. So what are we left with as an answer? We are left with n minus 1, n minus 2, all over 3 factorial. So let's have a look at what we've discovered and see if there is a pattern. Yes, there is. So n choose 0 is equal to 1 for any value of n. n choose 1 is equal to n for any value of n. n choose 2 is equal to n multiplied by n minus 1 all over 2 factorial. n choose 3 is equal to n multiplied by n minus 1, i.e. the number preceding n, multiplied by the number preceding that number, which is n choose 2, all divided by 3 factorial. So could you predict the value of n choose 4 based on the pattern that you can see? Have a go, see if you can write it down, and then you can check if you are correct. Yes, it's n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, and then the whole thing is divided by 4 factorial. So you might be asking yourself, well, what's the value of working that out? Surely as you work out more and more terms, this starts to look more and more complex. Well, let's have a look at an expansion, a very simple one. 1 plus x to the power of n. So, what would this expansion look like? We're going to write out the terms, and I'm going to do them as stacked terms vertically for simplicity. So, we would always start with n choose 0. We then take the first part of the expansion, 1, and I'm going to raise that to the power of n. We then take the second part of the expansion, which is the x. Of course, we need to make sure if it's a negative, we include a negative sign as well, but I've kept it as a positive for simplicity, and that will be raised to the power 0. Now, the second term in the expansion would then be n choose 1 multiplied by 1 to the power of n minus 1 multiplied by x to the power of 1. the next term is then n choose 2 multiplied by 1 to the power of n minus 2 multiplied by x squared. Let's do another one. The next term would be n choose 3 multiplied by 1 to the power of n minus 3 multiplied by x cubed, and so on until you complete your expansion. But we can simplify these terms. Let's see how. Let's take the first term. What did we say n choose 0 was equal to? We said n choose 0 was equal to 1. What about 1 to the power of n? Well, that's also equal to 1. And what about x to the power 0? That's also equal to 1. So this term just becomes 1. What about the next term in the expansion? What happens to that? Well, what did we say n choose 1 was equal to? We said it was equal to n. What's 1 to the power of n minus 1? It's equal to 1. And what's x to the power of 1? Well, it's equal to x. So how does this term simplify? Well, you have a product of n, 1, and x. So it simplifies to n multiplied by x. And we can do something similar in each of the following examples. In each case, 1 obviously simplifies down to 1 whenever it's raised to any particular power. The third term, we know that n choose 2, we worked it out, is equal to n minus 1 all over 2 factorial. But this is now multiplied by x squared. And the next term is n minus 1, n minus 2 all over 3 factorial multiplied by x cubed. So we have created another expression for the general binomial expansion, which tells us that if we are expanding 1 plus x to the power of n, this expansion can be written as 1 plus nx plus n minus 1 x squared over 2 factorial plus n minus 1 n minus 2 x cubed over 3 factorial, and so on. Now we're going to have a look at performing an expansion using this version of the binomial expansion. Now let's have a look at a quick example. Now we're going to expand 1 minus 2x to the power of 4, so you can all see that n is equal to 4 here. Before we start, it's worthwhile just making a note of something. If you're going to use this form of the binomial expansion, this part, which is here, has got to be equal to 1, otherwise you can't use this. The whole expansion we did was set up so the first term was equal to 1. So we've got this in the correct format. We have 1 minus 2x to the power 4. The second part of the expansion can be absolutely anything, because all that will happen is that wherever I have an x, I will replace it with what is in my expansion, which in this case is negative 2x. So let's get started. I'm going to stack the terms vertically again. So my first term is equal to 1. Now my next term is going to be n times x. So my n value is 4 and x here is represented by negative 2x in the expansion. What's my next term? It's n multiplied by n minus 1 multiplied by x squared, which is negative 2x all squared, all over 2 factorial. I'm writing out perhaps more working than I might do really, just to give you a very clear idea of what we're doing. The next term is n minus 1, n minus 2, all multiplied by negative 2x, all cubed, all over 3 factorial. And the next one will be n minus 1, n minus 2, n minus 3, all multiplied by negative 2x to the power 4, all over 4 factorial. Now, we then need to simplify each of these terms, which can very easily be done. So we have 1 minus 8x. Now again, be very careful as you're doing these expansions. So remember, over here, negative 2x all squared will be 4x squared, and you're multiplying it by 4 multiplied by 3, which is 12, and it's all being divided by 2 factorial, which is 2, so this term will simplify down to give you 24x squared. So the next term is a positive 24x squared. Let's take a look at the next term over here. So your negative 2x cubed will give you negative 8x to the power 3, and we're multiplying by 4, by 3, and by 2, and we're dividing by 3 factorial, which is equal to 6. So this simplifies down to give us negative 32x cubed. And why don't you have a go at simplifying the last one and then check your answer. So hopefully you've got this correct. The final term is 32, positive 32x to the power 4. And here is our expansion completed using a slightly different method. So we're now going to have a look at this expansion in its generalised form in more detail, because, as you will discover in the next lesson, we can use this expansion to expand expressions even when n is not a positive integer. So yes, if n is negative, we can create a binomial expansion. If n is a fraction, i.e. we're looking at a root, we can create a binomial expansion. If n is negative and a fraction, we can still create a binomial expansion. And this result, this general rule, allows us to create an expansion for any value of n. Now, if we're going to use this to perform an expansion, then this part here has got to be equal to 1. And if it's not, there are some steps that we have to take to ensure that we have a 1 there. Now, something that you are going to learn about in much more detail in the next lesson is that when n is a positive integer, this expansion will give you a finite summation of terms. If n is anything other than a positive integer, so if n is negative or a fraction or both, then you end up with an infinite series. Now, this is only valid if x is between negative 1 and 1. Now, this may not sound like it makes a lot of sense at the moment, but it will all be unpacked and explained in the next lesson. So let's just repeat that. If n is a positive integer, this will result in a finite series of terms in your expansion, exactly like the last example that we just did. However, if n is not a positive integer, so let's imagine n is negative 3, or n is equal to negative a third, or n equals a quarter, then this expansion is only valid if x is between minus 1 and 1, i.e. mod x is less than 1. Think back to the modulus function topic. Now, this may feel completely abstract, so you really need to see this in context in an example, but that will come in the next lesson. So for the moment, make a note of all this and be ready to explore this in much more detail in the next lesson.